Uh, Hey Tony, today we're gonna see what different types of the sequences. Majorly the types like a bounded sequence, bounded sequence. Mm, another one, another type is called monotonic sequence. Okay, monotonic, and there are two more concepts that we study in this session. There are two theorems which can be widely used to solve the sequence problems on the sequences. So without any ado, we'll get to there. What is monotonic sequence? Or what is the bounded sequence? Okay, we'll see about that. So what do you say that it is bounded? A sequence is bounded. First of all, let's take a sequence an, right? In this sequence a1, a2, a3, and so on, infinite number of terms are there. So what is bounded means in the sequential matter. So each and every number here is called the term of a sequence. Okay, term of a sequence, right? So what does the boundedness? Boundedness means it is confined. The sequence is confined, right? This sequence is confined. In what way? We have to find. So there are two ways to confine a sequence. First thing is confine its number of terms, right? So anyway, a sequence has an infinite number of terms, so this can be true. Next thing is confine its each and every term, right? So this can be possible here. This can be possible. How do we do that? Is, let's say, take a term. Let's define a sequence. Bn is a sequence where each bn is less than 100, greater than 0. There are two numbers here. We define like this. Okay, so each bn for all n, you can say this for all n. For all n, this is true. That means we can define that bn as which is greater than 0. So it is 1, 2, 3, 4, up to so on 99 you can do, but it cannot reach 100 because the limitation is less than 100. So you can keep repeating this 99. You can also define like this the bn, required bn, or else you can have our 2 plus 1 by n. If you define a sequence like this, then it is 2 plus, if n is 1, this is 1, 2 plus 1 by 2, 2 plus 1 by 3 and so on, which is strictly each and every term of Bn here is less than or equals to 3, greater than or equals to 2, because when the limit of this sequence is 2, so that's why we put the equality, but it never reaches. If we strictly speaking Bn is less than or equals to 3, which is greater than 2, the sequence reaches the 2 at the infinity, but you cannot, what do you say, you cannot approach the infinity. That means you cannot go to that destination of infinity. So Bn is always greater than 2. Infinity is not reachable. So that's why in that sense I am saying it is strictly greater than 2. Okay, so here in this sequence Bn, each and every term is confined, right? Each and every term is confined. So if in any sequence, so we say such sequences of Bn are called bounded. What do you say that? That bounded. So if in a sequence each and every term is confined by two real numbers, then we say that such sequences are bounded. Then we call that the sequence is bounded, right? So we know what is bounded. So we what do we do is we explore this definition much, okay, and we will give some of the examples. See, this is one of the example, this is another example. So we gave the bounded sequence if there exists confined by two real numbers. So this one, observe this one closely, this can be misunderstood as that can be very easily misunderstood. So for suppose you cannot use for different terms of the sequences two different real numbers, you cannot use that. So that means for suppose if b1 is less than 100 and greater than minus 100, b2 is less than 200 is greater than minus 200, you cannot use for different terms a different limit, what is that, bounds, you say that bounds, you cannot use such different bounds like that. For a sequence there are two bounds, one is lower bound, one is upper bound. So we define if for a sequence an there exist two real numbers small m comma capital M such that each an is less than or equals to capital M, greater than or equals to small m for all n. For every n is in between capital M and small m, then we say that the sequence an is bounded. right? So the sequence is bounded. For suppose, for examples, we gave two examples earlier. So now we go to if there is no such small m existed. Okay, if there is no such small m, this small m is not existed. That means if there is a sequence bn and a real number capital M such that Bn is less than or equals to capital M for all n, then we say that the sequence is bounded above. So then we say the sequence Bn is bounded above. That means there is an upper limit. So see this, in each and every term of the Bn cannot exceed the capital M here, right? Any term of the sequence cannot exceed the capital M. Such sequences, if there is a bound, this is called the bound, okay? Particularly, every term of the sequence is less than this bound, we say this is called upper bound. What do you say this? This M is called particularly upper bound, okay? So all this term is not mentioned in your textbook, so don't bother much, just see what it is, which is bound and it is higher, right? Every value of the every term of the sequence is less than this one, so we call it as an upper bound. Similarly, we call this m, small m is called lower bound. So a sequence which is having an upper bound is called bounded above. Example of such sequences is, example, let's say minus n. If we define a sequence like minus n, this is nothing but minus 1, minus 2, minus 3, and so on. It goes to the minus infinity. So each and every term of the sequence is less than 0. So if we want to take a real number, so define the sequence as an. Okay, each an is less than 0. So this sequence is bounded above. Bounded above, you can call it. For another example, n square minus n square you can define something like this: an okay, just wait, let us define another sequence minus n square. This is one of the simple sequence, okay? So in this, the terms will be like this: minus 1, minus 4, minus 9, the square of n square. So it will be like this: minus 16 and so on. Even in this, each and every term, you say this bn, each and every term is less than 0. So this sequence is also bounded above. See here, the upper bound is, you can call it here, is 0. But see, this is 0 and this is minus 1 in the coordinate axis, right? Each and every term of the sequence, okay, and not in the coordinate axis. You can visualize like this: minus 2. See here in the above example, we can use this one in the above example here. See, each and every term is like this, -1, -2, and so on. It goes in this way. So any value which is greater than -1 can be used as an upper bound. You can use -0.5 as an upper bound. You can use -0.2575 as an upper bound. You can use -0.25 as an upper bound. So there are so many upper bounds if one bound is existed, right? It may not be the there exists a unique number. You cannot say this need not be the unique number. There may be exist so many numbers. So if this is a finite m, there exists, it is obviously less than m plus 1 also, right? So there may be exist so many upper bounds, but we need the concept of bounded above. So similarly, we can define a sequence of bounded below sequence. Okay, like how we define bounded above sequence, we can also define bounded below. See this is bounded below, as you say. If a sequence an is said to be bounded below if there exists a real number m belongs to a real number r, real number system r, such that an is not less than, it is greater than or equals to m for all n. Okay, then we say that the sequence is bounded below. That means each and every term of the sequence is always greater than or equals to the our number m. This is lower bound. You can say this is called lower bound. Okay, this number is called lower bound. We can give such examples of that sequence. Let's take a simple sequence n. So sequence of natural numbers 1, 2, 3, 4, 5, 6, and so on. Each and every number in this sequence is always greater than 0. Okay, let's take another example. 1 plus 1 by n. In this sequence, each and every term is 1 plus 1 by 1, and second term will be 1 plus 1 by 2, and so on. So each and every term in this sequence is, see, when at this, if the sequence is reaching the infinite point, then its limit is going to be 1 plus 1 by infinity. This is 0, so it is reaching towards the 1, so each and every term in this sequence is always greater than 1. Okay, 1 is acting as a lower bound here. So since as we discussed how the upper bound is not unique, in the same sense the lower bound is not unique. Lower bound is not unique. So If 1 is the lower bound here, take any number which is less than 1, that is also acts as the lower bound. So 0 is also another lower bound, minus 1 is also another lower bound, minus 2 is also another lower bound. So you can have infinitely many lower bounds here. So this is the what do you say, that behavior of the bounded sequence. Okay, and we define. So now let's sum it up. What is the bounded? So if we say that a sequence is bounded, it must be bounded above and bounded below. So if we say that sequence is bounded above, so each and every term of the sequence is less than m. This is, there exists an upper bound. If we say a sequence is bounded below, so each and every term is always greater than or equals to small m. Okay, then we studied three types of sequences. Now let's move on to the next concept, that is called convergent sequence, right? And not the convergent sequence, the monotonic sequence. Monotonic monotonic NIC sequence. What is this sequence? Monotonic sequence. A sequence, see this monotonic, what does the name suggest is it has an uniformity, right? So a sequence is increasing or decreasing term by term. We call such sequences are monotonic sequences. So they follow a certain rule. Let's take a sequence an where each term a1 is less than or equals to a2 is less than or equals to a3 and so on. See this, if a1 is 1, you can say a2 is 2 or greater than or equals to 1. Okay, so you can say this sequence is, so the each and every term, the next term is at least higher than a3. Let's take a3 is higher than a2, or at least it is equal to a2, and it cannot be less than a2, right? So this type of behavior of the sequence is called monotone. Okay, so there can be another contrast behavior bn. See this, you can say that b1 is greater than or equals to b2 is greater than or equals to b3 and so on, right? Here the second term is always less than or equals to the first term. That means the consecutive term here, consecutive term is less than consecutive term is less than previous term. You can say that less than previous term, or simply you can say that bn is greater than or equals to bn plus 1. So this is the mathematical representation of this sentence. Similarly, you can define here as an is less than or equals to an plus 1. See, these two are different contrast of that monotonic sequences. See here, the sequence is here term by term. For each and every term it is getting higher and higher values. Okay, so at least it is not decreasing, it is getting higher and higher values, assume that. So such sequences are called increasing sequence. Okay, let's say monotonic increasing sequence, monotonically increasing sequence. See here, this sequence is getting term by term decrement, so we call the monotonically decreasing sequence. So either any one of these sequence can be called as a monotonic sequences. Okay, so here see this sequence is term by term decreasing, here in the sequence is term by term increasing. Any one of these sequences can be monotonically called monotonic sequences. Okay, for let us give some examples here. Like we said that capital N, the sequence of natural numbers which is increasing 1, 2, 3. This is monotonically increasing sequence. And let's take another sequence 1 plus 1 by n and minus n 1 minus 1 by n e to the power of 1 by n. Let us examine what are these sequences. See here, this sequence is the first term is 1 plus 1 by n 1 by 1. Okay, the second term is 1 plus 1 by 2 and third term is 1 plus 1 by 3. So it is continuing like this. See, the first term is greater than the second term and second term is greater than the third term. So this sequence is monotonically decreasing. Okay, so call we call this, we shortly call here monotonically decreasing sequence, MD. Okay, here monotonically increasing sequence, MI. We write here like that. See, this is monotonically increasing sequence. This sequence is monotonically decreasing. And see what this is, minus 1, minus 2, minus 3 and so on, minus 4, write this one. So minus 1 is greater than minus 2, minus 2 is greater than minus 3 and so on. It is like decrement, so it follows this rule. So we say that this sequence is monotonically decreasing. Let us examine the next example. See this 1 minus 1 by 1, this is 0, right? 1 minus 1 by 2, 1 minus 1 by 3 and so on. See, this is half, this is 2/3. So each and every term is increasing here, and there will be no fluctuation at 100 in between any value in this monotonic sequences between any two terms. It only increases or decreases, right? So see here, see this is term by term increment is happening. We call this as a monotonically increasing sequence. We examine the last one. So e to the power of 1 by 1, that is e to the power of 1 by 2, e to the power of 1 by 3 and so on. You see this, e to the power of 1 by 1 is nothing but e. This is root e cubed root e and so on. So the sequence is decreasing by term. We call that as a monotonically decreasing sequence. Okay, we give Mm, okay, let's say. Now, so far we define two types of sequences, right? Bounded, bounded type, and monotonic type. So, let us examine this one. What does those graphically means? What are those graphically means? So, bounded means, let's see this graphically. If you okay, see what are those graphically means? You can see this here. Bounded, that means if a sequence an and each an is less than or in between a lower bound and upper bound. Let us assume that. So for this is 1 and 2 and 3 and 4. Let's say on the y axis you mark small m and capital M. Okay, so any term of the sequence, let us say any term of the sequence must be in between these two lines. Okay, these two lines must be in between these two. Any term, this is second term, this can be third term, this is fourth term, fifth term, sixth term, and a term cannot go above this line. Okay, and cannot drop below this one. Okay, such things cannot happen. So this point can be here, this one, these blue points cannot be happen here. Okay, so that is what the bounded means graphically. Now we see what is the monotonic means graphically. So this is 1, 2, 3, 4, 5, 6, 7. Okay, see here, this is, let's check, this is the first point here. Okay, first point is having a value, let's say 2, and the second term of the sequence can be equal if it is monotonically increasing sequence. Monotonically increasing sequence, you said. So the second point can be equal to 2 or it can be higher than 2. Third point, if it is 2.5, third point can be equal to 2.5 or it can be little bit higher. Okay, fourth point also like this. It is so the curve is gradually increasing here. Okay, you can say that, or it can be, or the curve can be constant because of the existence of equality sign. We said b1 is less than or equals to b2 is less than or equals to, because of this equality signs, this equality signs, the curve can also be act as the constant here. Okay, this is what this means. So the curve of the graph can increase or it can go slowly and then reach the constant, or it can increase very steeply, very steep. That increment is so steep, the not a very less steep, increasing slowly, you can say that. This is the graphical point of view of those sequences. Why? Because I am explaining this graphical approach, because the next theorem is very valuable to us. Okay, what does it say is, A bounded monotonic sequence is convergent. A sequence is bounded and also monotonic, then it is convergent. Okay, a sequence is bounded monotonic, so bounded plus monotonic implies the convergent. It cannot be the other way around. It cannot be the other way around. We can also have the counter example for this case. Now we see a sequence is we see the proof graphically here. I am not going to explain the proof there, but you can sense it by the common sense itself, by the graphically. Okay, see, a sequence is bounded and monotonic, they say. The sequence, let's say, graphically it means bounded and also the monotonic. Okay, so let's say it is bounded, that means there exist two real line bounds that it cannot cross. Two lines that a sequence cannot cross. Okay, it is said that so these two represent the boundedness of the sequence. Now we say that sequence is monotonically increasing. So we say monotonically increasing or decreasing. We can have the both the cases here. Let's find. Let us assume that it is monotonically increasing. In the first case, it is monotonically increasing. That means let's see the graph of the curve is increasing, so that it does not have any. For suppose if it is increasing, it crosses this line, but the boundedness stops this increment, so it cannot cross this line. It cannot cross this line. So the increment must be halt somewhere. So that means it cannot cross the red line, so the increment is becomes very less and less and less for the increment becomes very less and less, so that so as it reaches any limit, any constant, whether it is m or any point less than m. Okay, so it must reach, let us assume that it is reaching m, so the increment becomes very less term by term, and it reaches the m at the infinity. Okay, this is one way to use. In the similar way, this graph is also decreasing, and then it cannot decrease further than the small m, so it has to decrease its decrement and to reach a certain limit there. Okay, this is the graphical explanation. So we can have problems on this. We will solve those problems. Before that, we will see a squeeze theorem. Okay, a bounded monotonic sequence. So that this theorem is used. A bounded monotonic sequence is convergent. Okay, so this theorem is useful in the problems where if you cannot find the limit an. Okay, if the limit n tends to infinity an. If you cannot find this, if you unable to find what is the limit, then see its boundedness. If it is bounded, you see that, and is it monotonic, you see, then you can say it is bounded plus monotonic, so it is convergent. But we don't know its converging limit, okay, but still it is convergent. You can use this theorem to the problems in such a way in such a way. So as I said previously, the other way it cannot happen. We can give the counter example for that. Let's say uh, minus 1 by n whole to the power of n. Okay, sequence nth term is defined like this. So what does this sequence represent? See this here. If n is 1, so it is 1, this is 1, this is minus 1. So first term will be minus 1. If n is 2, 2, 2, so minus 1 by 2 whole square, that will be 1 by 4. Third term will be minus 1 by 9. Fourth term is 1 by 16, and so on. See this. So find its limit. The limit n tends to infinity, minus 1 whole to the power of n by here it is not 9 and this is 3 cube. Okay, this is 4 to the power of 4 and so on. So this is n to the power of n. Okay, so when n tends to infinity, so whether this n, for suppose if you substitute this n equals to infinity, this is a finite term. Okay, if n is positive, then we have minus 1. If n is even, minus 1 to the power of even is 1. If n is odd, this can be negative 1, right? So it can be 1 or negative 1. So if n tends to infinity, the denominator gets too high that it is reaching infinity very faster. So infinity is in the denominator. So whatever is in the top in the numerator, that is a finite value, that the denominator tends to infinity. So the net value is going to be 0. Okay, you can see this is approaching towards the 0. This is a convergent one, and it is bounded definitely, but not monotonic. Monotonic, you can see that first term, why it is not monic, this you can see that first term is always less than the second term. Here the second term is greater than the third term. Third term is less than the fourth term. So it is not maintaining the same inequality throughout the sequence. So so it is not monotonic. You can say that. We get to know the problems. I suppose there are two more things. Yeah, deal that. We'll deal with that. The sequence. Okay. There are two more concepts are there. The squeeze theorem, or you can say that a squeeze or sandwich theorem. Squeeze theorem. Okay. Or sandwich, you can also call this as sandwich theorem. what does it say is we have a three sequences. Let's say an one sequence, bn is another sequence, and cn is third sequence. And each and every term of this sequence, you can say bn is less than or equals to cn and greater than or equals to the an. That means bn is in between an and cn. You can see that. That means, see this, if you substitute n is equals to 1, b1 is in between a1 and c1, b2 is in between a2 and c2, b3 is in between a3 and c3. So you can see that term by it is bn is termly bounded by these two sequences. Okay, if it is happening like this and these two sequences an and cn converges to the same limit, to a limit L, then Bn also converges to L. You can see this. If An and Cn converges to the L, then Bn also converges to the L. Okay, so you can understand this one like this. This is A1, A2, A3, not like this. C1, C2, C3, and so on. A1, A2, A3, B1, B2, B3. So B1 is in between A1 and C1, A2 and C2, A3 and C3. You can see that if you explain this graphically, A1, A2 and so on, these are converges to the limit L. C3 is also converges to the limit L. That means infinite point in this sequence is reaching towards the L. Okay, infinite point in the an sequence reaching towards the L. So the infinite point in this sequence in between cn and c, in between c and a, so it is also has to reach the L. So you can see, okay, so if you see the graphically, if you see it graphically, let us explain this sequence. So first, suppose an is a sequence something like this. Okay, let's say it is reaching f5. Cn is, this is, let's say this is Cn. Let's say this is 5. The Cn is decreasing so as to reach this one. Okay, and our Bn is like this. Let's say the graph of the Bn is like this. Okay, when an is, so this graph of the Bn, the green curve is squeezed in between the blue line and the red line, so that if the red line and blue line reaches the limit 5, then the green, then these two lines squeezes and it restricts the green line to reach the 5, to converges to the limit 5, right? So that's why it is called, see that green line is sandwiched between the blue and the red graph. So it is called, that's why it is called sandwich theorem. okay, and it also squeezes this graph so that it must be reaching the same limit, so it is called squeeze theorem. The applications of this is enormous, and the basic mathematical definition will be like this, and graphical analysis is like this, or term by term analysis is like this. And let's go to some examples here. In the textbook it is given that one or two examples, okay. So example, so example is given a sequence defined as cos n by n square, okay. So this is the sequence you can see. So the cos x, what is the bounds of the cos x function? It is having an upper bound as -1 and lower bound upper bound as +1 and lower bound as -1. So cos x, the function cos x is in between -1 and 1, right? So cos n is also in between 1 and -1. So cos n by n square is in between 1 by n square minus 1 by n square, okay. Like in the previous example, this is our an and this is our cn, this is our bn. Let's see, if n tends to infinity, an is going to be -1 by infinity is 0, cn is also going to converges to the 0. If an and cn converges to the 0, then bn must converge to the 0 by the squeeze theorem, okay. That's how you use this squeeze theorem, okay. You can say by the squeeze theorem. You can refer to the textbook for this, because the explanation, let's say, limit mathematical explanation will be like this: limit n tends to infinity, -1 by n square is nothing but -1 by infinity, that is 0, and limit n tends to infinity, 1 by n square is 1 by infinity, that is 0. So by squeeze theorem, you can say that by squeeze theorem, cos n by n square converges to the 0, okay. Let's say this is our logical explanation and this is mathematical explanation, so that when you write the proof, you write in this way, okay. And there is another beautiful function, okay. Oh, let's see, that would be very beautiful there. See, any sequence an is represented by the dots in the R2 plane, right? So let's say this an is written like this. So let's say this is the dot and this is the dot. This is second term, third term, fourth term, fifth term, sixth term, seventh term, eighth term. Right, like this. So we say that there exists a continuous function which contains the terms of the sequences, okay, which contains the term, there exists a continuous function which contains all the terms of the sequences, which continuous, it is said continuous, so it must be continuous graph. It cannot be like this. there exists a continuous function f of x, that the functional value at this one, see this f1 is equals to the a1 there, so f1 is equals to a1, here 2 f2 is equals to a2. So when you continue like this, you get f of n is equals to an. Okay, so this is the continuous function which can define contains this sequence an. Okay, now what is the use of this one? Okay, we define this one like this, right? Okay, so for suppose if we can also define another continuous function. Okay, this is one type of the continuous function which combines the sequence with a function continue, which combines the sequence with the continuous function. Okay, this is one of the concept which combines the sequence to the continuous function. In the next concept we will see that if there exists a sequence an which converges to the limit L, if there and f of x is another continuous function, let's say this is g of x, g of x is, this is the second concept, another continuous function, another continuous function, right? Then g of an, if you take this sequence, this is also a convergent sequence, and this sequence converges to the limit g of L. Okay, it says something like that. So if an is converges to the L and g is a continuous function, g is continuous function, then g of an is continuous to the L. So here you can see that g of an means you substitute each and every term of the sequence in this function and generate another sequence. Let's say suppose an is, for example, if you take an example, we'll define an is given as 1 plus 1 by n. This is a convergent sequence which converges to the limit 1, and x square plus 1 is a polynomial function. Polynomial function is continuous as far as we know. No, sorry to say something like that. As we know that it is a continuous function throughout the, what do you say, that real line. So you substitute each, and this is defined as g of x. So g of an is, that means you substitute, this is an, substitute an wherever x is there. So you substitute 1 plus 1 by n plus 1. So wherever x is there, you substitute an. It's a general term, so it can be, so 1 square a square plus b square plus 2ab plus 1, that is gives the g of a to the power of g of an. Now 1, see this is 1, this is 1, sum those two up, it gets 2. 2 into 1, that is 2 by n plus 1 by n square. Now this is g of an. Now take the limit n tends to, when this is a sequence convergent or not, we will see. Take the limit n tends to infinity, limit n tends to infinity, g of an is limit n tends to infinity 2 plus 2 by n plus 1 by n square. See here, substitute infinity here, this becomes 0, this is also 0, so we are left with the 2. Now what is g of 1? G of 1, so it is 1 square plus 1, that is nothing but 2. So here g of an is another sequence which converges to the g of an is another sequence which converges to the g of 1. Okay, that is the example of that. So it is, the examples are made in such a way that so you understand the theorem very well by a simple approach we know. Okay, by the simple examples we know. For suppose if we see this, if we know this one is given and they ask, the sequence g of n is given and they asked you to find what is its limit, then you examine the an whether it is converges to the L, then you directly substitute the sequence directly converges to the g of L. Okay, so let's see some of such examples. Let me design one such example. Is, let's say, sine n square, not n square, not n square, let us define, that is 1 by n plus cos 2 plus n by n square. Okay, our sequence is defined like this. See this, even just by looking at this we will be saying that even this is so simple than what we are expecting, but this is gives you a glimpse of what our previous theorem can be, our previous continuous function previous theorem can be. Okay, what let it be. So this first term is sine 1 plus cos 2 plus 1 3 by 1 cos 3. Okay, and the second term can be something like that, and third term. Okay, you see whether this sequence is convergent or not. Okay, let us examine this one. First examine this one. Okay, sine 1 by n. Okay, sine x is a continuous function, as we know. This is a continuous function. Okay, let's say this is an. Let's consider this as the an. So the continuous function of an is given here, but an is converges to the 0, So the sine of an converges to the sine of 0, that is 0. So sine 1 by n is converges to the 0. Similarly, you can examine cos, another example, cos 2 plus n divided n square converges to what? So let's see this one, the term which is inside here, bn. Let's consider. As we know, the cos function is continuous. 2 plus n, okay, when n tends to infinity, bn is 2 by n square plus n by n square, that is 1 by n. When n tends to infinity, 2 by infinity plus 1 by infinity, that is 0 plus 0, that is 0. So bn tends to 0 as n tends to infinity. So cos of bn also tends to cos 0, that is 1. Okay, by the algebra of the limits, what do you say? There are two, if two sequence, if a in one sequence, bn is another sequence, an converges to l, bn converges to the m, then the sequence an plus bm converges to l plus m. You can see this sequence is converges to 0, this sequence is converges to the 1, but the given sequence is sum of these two. So the given sequence sine 1 by n plus cos 2 plus n by n square converges to 0 plus 1, that is 1. The 0 is this one, the 1 is this one, limit here. So it will be finally converges to the 1. That is how it is useful. In the next class, we will try to do so many problems. Okay, for you, Tony. So we stop here.